Now we have Haggai Liu from Simon Fraser University, who will be talking about enumerative properties of Cogrowth series on free products of finite groups.
Okay, may I begin? Okay.
Go for it.
All right. So yeah, this talk is based on my thesis that I recently defended. It's a master's thesis. So the main problem we're talking about is a word problem. It's the phrase as follows: we're given a group that's finitely generated and a generating set S. Determine if a given product of elements in S evaluates to the identity element. And to help us study this, we're going to introduce notation for the language of the word problem. Notice we're distinguishing between symbol concatenation and group multiplication. Okay, so what's a Cogrowth? Well, again, let's take G to be a finitely generated group with a finite generating set S, but it shouldn't contain the identity element. And here we define a Cogrowth sequence of the group G with respect to S is just this, the counting sequence of our language, given that counts kind of how many words of length n is in our language. And its associated generating function is called the Cogrowth series. Okay, so what we're going to do is continue the study of Bell and Mishnah, with Dr. Mishnah being my advisor. So we're going to study the specific case of a free product of finitely many finite groups. So we're also going to restrict to the fact that each of our free factors is cyclic or dihedral. So an important fact we must state is the free product of finite groups, they have algebraic Cogrowth generating functions. So that means that there exists some polynomial with integer coefficients q, t, z. That's obviously not identically zero. That solves our Cogrowth series f of t. And we'll call q a satisfying polynomial. And if its degree in the z variable is as small as it possibly can, we'll call it a minimal polynomial. So our main goal here is to just obtain a bunch of results and bounds on this q that we just defined. Okay, so here's an example of one of the major theorems we're going to look at regarding cyclic groups, and I'm going to define some notation in a sec to lead to this result. But essentially, the table you see in front of you here gives an upper bound on the degree of q in the z variable in this particular case. Okay, so to visualize this problem, we will use Cayley graphs. I'm sure you guys are all familiar with that. So this is a directed graph actually, where the vertices are the group elements and the edges show multiplication by elements of our generating set S. So hence walks do in fact show the products multiplication of elements in S. So we're going to take excursions to be walks that start and end at the vertex. That's the identity element. Of course, it just has to start and end at the same vertex, but we'll choose one. It doesn't matter since the Cayley graphs are vertex transitive. What's important is our Cogrowth sequence just counts the excursions on this the associated Cayley graph. All right, so given an example of a finite cyclic group of order n generated by a single set S, we see our language is just concatenations of x, where length is a multiple of n. So Cayley graph is a directed cycle with n vertices. And we have that here. And then the Cogrowth generating function is simply a geometric series. In a not so easy case, we'll look at the dihedral group that's with its standard presentation, generated by a rotation by the smallest angle and a flip across an arbitrary axis, right? And for n equals 3, the symmetries of a triangle, we see that a Cayley graph looks like this. And what is a Cogrowth generating function? It's not easy to tell just by looking at the Cayley graph. So we actually have to do some work here, but the proposition in front of us here gives us indeed the formula we are looking for. Okay, so as you can see, it's much more complicated than just a geometric series. And as a corollary, if we were to simplify equation 1 in front of us, we can actually, into a ratio of 2 polynomials over the integers, we actually get the degree of both our polynomials to be the same, and that's upper bounded by a quantity that's roughly n over 2. Okay, so with a collaboration with my advisor and another prof from University of Waterloo, we came up with a general bound using representation theory. So this applies to any finite group with any generating set. And we use a degree of irreducible representations to get a bound in this case. However, this can be seen as a first bound in our case, but it's not optimal in general. So in the cyclic case, we do have one of our P and Q achieving equality, but for the dihedral case, the bound that we just saw here is pretty weak, because the corollary one we showed you from the explicit formula gave us much stronger bounds. Okay, so let's talk about free product of finite groups. Well, okay, so here's the definition of a free product of, say, M groups, right? And then what's important here is that the non-identity elements in different free factors do not commute with each other. So there's no commutating relation in that sense. So for example, if I take 3 copies of Z2 or Z mod 2Z, we see that if they're generated by X, Y, and Z, then we must have, for instance, X, Y, and YX not equal. Okay, so what's important here is the Cogrowth generating function of G depends on that of each of the GI, but non-trivially. So what I mean here is if I know the answer for each of my free factors, I know the answer for my free product, but the way we get the answer is not that straightforward. Okay, so yeah, again, we'll focus on the case where each of our free factors is finite, and we'll even take our generating set to be the disjoint union of the ones taken for each of our free factors. So here's some visualization of Cayley graphs, which are basically infinite fractals for 2 free product, 2 cyclic groups. And the structure is a bit more complicated if I involve a dihedral group here. Okay, so to get into our main result, we'll first need to define what a resultant is, because we need to use those to eliminate some variables. And we define resultant to be a determinant of what's known as the Sylvester matrix. This you can look up. The construction is kind of messy, so I didn't define it on the slides. So with resultants, though, we just care that we have this kind of upper bound on the degrees with 2 variables here. And we'll use that a lot to establish upper bounds for our minimal polynomials. And we'll also define reduced resultants. And the reason for that is, well, monomial factors that appear in computing resultants are not significant in general. So we need to remove it whenever we can. And also, if we have redundant exponents, we want to remove that because that's not really going to help us in any sense. Okay, because we want our degree upper bound to be as small as possible. So here's an algorithm for algebraic elimination. And so what's special about this is that at each stage, we just repeatedly apply a reduced resultant computation rather than the classic resultant. And at the end, we just keep going until we only have 1 polynomial left in our system of equations. And then that gives us a satisfying polynomial. And so here's the notation for free product of cyclic groups. What I'm doing is I'm taking R to be the number of distinct cyclic factors. So each of them might have many identical copies. And we'll take, for each of our copies, we're going to take exactly one generator element and together collectively form our generating set. And we'll use free probability. We get this major theorem that's coming up now. So here, if I have the G and S as I just described, then we simply need to solve a system of R+1 equations and eliminating these extra variables Z1 to Zr to get a polynomial with respect to T and Z. And that gives us our satisfying polynomial, a satisfying polynomial in this case. And so for the case of R = 1, this is actually pretty easy. Because this is already solved by the paper by my advisor using a different technique. And here's what they get for their satisfying polynomial. And notice if I run the algorithm, I get exactly the same one. Okay. And the key observation is this degree here is independent of M, which means the number of identical cyclic factors don't actually appear as exponents. They only appear as coefficients. And this is actually true for an arbitrary number of distinct free factors. And so for R = 2, we get something similar. As you can see, once I run one iteration of my algorithm, the polynomial will look different based on the cases of M1. But it's already a bit more complex. And the satisfying polynomial we get is kind of too complex to generalize. But we do we can get a naive upper bound by using that resultant inequality. However, here's that theorem I showed you again. And what happens at this, we attain some upper bound that's less naive. And the way I did it is also I obtained a lower bound on the valuations of resultants. So then this is just a direct subtraction. And with the help of that, we can generalize it for general number of distinct cyclic factors. So you see the equation 4 here has two inequalities. The second one's rather a trivial one that's symmetric, and the first one is kind of follows from our previous theorem here for R = 2. Okay, so yeah, that's just the thing. What we have here, and we actually have get some conjectures. For the sake of time, I didn't include all the details leading up to the conjecture. But one conjecture is the 4 entries in the tables we just saw, we can actually get rid of the 1+. I conjecture that, but I don't know it for sure. So the next one is if I only have two distinct factors and none of them is repeated, then we actually have a even stronger upper bound. And here are some plots to kind of back up our conjecture. You see the squares are the ones we got experimentally, and the circles are the ones we got our theoretical upper bounds that we just been discussing. So using representation theory, we get another case for general finite group and with generating set. Arbitrary finite generating sets. And important thing is that equation 4 we got, this theorem can be used to get the second inequality, but not the first one. So I got something slightly stronger, but this one's more general purpose. Okay, so let's take a little bit look at identical dihedral factors. So we'll take m copies of Dn, and each of them is generated by a rotation and a flip, as we saw before in the finite case. Now, obtaining the Q that we saw explicitly is a bit more difficult since the generating function for Dn is not geometric. So now recall this formula we had before from my first proposition. So I guess I should use n instead of m, but it doesn't really matter. And as you can see, degree we can get some degree bound for our satisfying polynomial. don't get confused that you saw P, but it's actually just the Q that we've been talking about. Okay. And with that, we lead to a conjecture regarding this particular satisfying polynomial here and the leading term in the Z variable. We have some, just by looking at some experimentally, we get kind of these 5 statements that seem to be true, but again, hasn't been proven yet. But I do plan to prove it in the near future. And so here's the general format of all the groups we've been looking at. Here's a summary of all the results for each particular variation here. So you can see most of the cases are still not yet, work has not yet been done, but in some of the simple cases, there are results from me, and there's one result from my advisor as well. And so just a summary of what we've seen here in this. In these slides. And here's some conclusions. So I'll just talk about the next steps. We need to, we may want to involve other classes of finite groups besides cyclic and dihedral. We might want to experiment with other generating sets. And we might want to ask about radius of convergence on Cogrowth generating function. So the paper by my advisor actually have some results on those for some different cases, but maybe we can extend that for future work as well, right? So yeah, and that's all I have for today. I see I have some chat because I wanted to make sure I finish on time. I just didn't read it until the end. Oh.
Okay, let's thank our speaker. Okay, does anybody have any questions for Haggai?
So I have a question. You showed us this very nice table of the cases that have been proven so far and the ones that are remaining. Do you have a sense of whether the open cases are difficult but tractable, or whether there's an obstruction in some cases?
Oh, you mean the table of summaries?
Yeah, your summary table.
Oh, it's just that it can be done. It just hasn't been looked yet. It's just now notice what I said is that adding extra dihedral factors makes things more complicated than adding more cyclic factors. Just because in the finite case, the generating functions don't look as nice. So just mostly the work hasn't been done yet. Haven't gotten enough time to do that, but I'm sure it can be done. And I do have a general conjecture for what this general format would give us, but I didn't display it here.
Thanks.
Okay, other questions? We have another minute or so. Okay, well, let's once again thank our speaker.